So welcome everyone. Today we have the pleasure to have Jozef Skokan telling us something about how to separate the path in a graph.
All right. Thank you very much. Thank you for coming. Yeah, I wanted to tell you a little story about a problem that we started to work on about a year ago. We made some progress, and then there will be a point when I tell you there was a day when a paper appeared on arXiv, and I almost got a heart attack when I saw it, because it seems like the old work was gone. But miraculously we recovered, and this is the story how we recovered. So, I will try to define all of this as we go, but I will start with some historical remark how this all started. So, there was a basic question in this area, and it was asked by Rennie in the early 60s. Okay, and basically what we have is we have a set with elements A1, A2, AN, and we want to somewhat distinguish between these elements of the set. Okay, so we will say that the system of the subset F1, F2 all the way to Ft. And again, all Fi's are subset of A. So this system, and I put here, weakly separates set A if the following property is satisfied. Whenever you take two elements A and B from A, you need to find a set in your system F with the property it can distinguish between A and B. Okay? So either A is an F and B is not there, or A is not there and B is there. Okay, so we would like to find something like this. And the question that Rennie asked was, what's the minimum T that you can find such a system? Okay? And his motivation was, of course, from information. Okay, so this is not too difficult to do something about it. Okay, and so what do we do? Well, so for every index I can look at the set Si, which will be the set of all indices, okay, such that Ai is in Fj. Okay, and what does it mean that the system F weakly separate? Well, it means that the sets Si must be different, right? You cannot have two elements for which these Si's are the same, otherwise you cannot distinguish between them. Okay, so F weakly separating is just equivalent that for every I not equal to J, Si is not equal to Sj. Okay? But these sets are the subset of the first T integers, and all these sets must be the same. So 2 to the T must be at least as big as n. Okay, and so that means T is at least log to n. And of course, if you think just for the second, you can easily actually show that this min T actually is equal to log to n. Okay, you can construct such a system quite easily. Maybe left as an exercise. Okay, so this is a weak separation. Now, Dixon in 68. Okay, he came with the concept of the strong separation. Okay, so here we just care to find one set that distinguishes between A and B, okay, but you don't know which one is it and which one is not. So Dickinson asks, so what changes if I really ask for one F that separates A from B and the other one that separates B from A, okay? So again, for every A and B, there exists F and F prime in my system such that A in F, A not in F prime, B not in F, and B is in F. Alright? And so what he proved, again, he would like to find minimum T such that this is possible. And what he proved was that actually it's roughly the same answer as over here. Okay, with some error term which is little. Okay. All right. I actually went as far as to pulling out this paper. Nice readable, does some clever thing. Okay, but then I came across a paper by Joel Spencer from 1972. And it was so beautiful that I just couldn't resist and just reproduce the proof. So I again consider these sets as I. Okay. But what does it mean that I have a strong separation? Okay. Well, if you think about this for a moment, strong separation really means that for every I and j, you cannot have that Si is a subset of Sj. Okay. Right. All right. So what does it tell us? Well, it tells us that S1, S2, all the way to Sn is anti-chain in 2 to the t. And we know exactly, well, what does it mean? Well, that means that n is at most t over t choose 2, t over 2, right? Okay, and well, if you get the minimum, then you actually get that this is, okay, you get the precise formula of what it should be, right? So it would be log to n plus 1/2 log n plus other two terms, and if I wrote it down, I would be just showing up, so I will not write it. There is something here, some constant plus below. Okay? So when you look at it, I mean, I hope you appreciate it. This is just beautiful. All right. So the talk would possibly end here because that really summarizes well, what you can tell about these two problems. But of course, you can make it more interesting. Okay, and how can you make it more interesting? Well, you stipulate some condition on this A, or you stipulate some condition on F, right? You put some restriction how this F should look like, possibly sizes of them, or you put some other structural condition on A and F, and then you try to see whether you get something more interesting. Okay? And this happened. Okay, and so for this talk, okay, my set A will be set of edges of some n-vertex graph. Okay, and as for the system F, we put some graph theoretical restriction on elements in that set F, right? And what will be such restrictions? For example, like the title suggests, you might request that all FIs will be actually passes, not just arbitrary collection of edges. Okay. All right. So some questions of this form were actually investigated from 1980s. But this particular question, okay, when we imposed that elements of F should be passed, was actually asked by Katona in 2013. So Katona, 2013. Okay, so find the minimum T if all FIs are passed in this graph. Okay, what can we say? All right. So what can we say? Also, there is some easy observation that we can do. So I would like to first convince you that our T can be of order n times log f. Okay? So I would like to show you that every graph can be separated, be it weakly or strongly, with n times log n times some constant r. Okay? And how am I going to do it? I will use, it doesn't matter whether we consider weak or strong separation, but what am I going to do? Okay. So again, A are edges of some n vertex graph. Okay, so size of A, okay, it's surely bounded by n squared. Okay, so regardless which of these results that we sort of introduce, we know that these edges can be separated by some set of edges where T is sort of order log 2 of size of A, right? And so this is bounded by, let's say, 2 times log 2n. Okay? So I can find constant log 2n sets of edges which separate all the edges. But of course, these are just the subgraphs. Okay. And I don't know, well, now I have to construct some path of it. Okay. And well, here it comes. So there is a result of Lobath from 68. Okay. And this result says that if you take any n vertex graph, then you can decompose the edges into n over 2 cycles or paths. Okay. N vertex graph can be decomposed into at most n over 2 cycles and paths. Okay? You don't know how many cycles will be there or how many paths will be there, but surely every cycle you can cut to paths. You have at most n over 2 of them, so that means you can decompose it into at most n paths. Okay? And now it's easy what I'm going to do. I take f1, f2, ft, each of them separately. Each of them is a graph of n vertices. Each of them can be decomposed into a path, and because this system of graphs separated all the edges, then this system of t times n paths will separate all the edges in the graph, and t by n is n times log n times log n. Okay, so we apply this again to every fi. Okay. All right. So we can get as far as n again. And now the question is whether we can do any better. All right. So there were two groups of people who worked on this problem roughly at the same time. Surprisingly, one group chose the weak separation problem and the other one chose the strong separation problem. So, okay. So, Victor Falgas-Ravry. The only problem with it is that each group had at least four people, so one needs to just stay all of them. So let me just write it. So Kittipassorn, Korandi, Letzter, Balogh, Narayanan. You can always wish they had a shorter name. Okay. So in 2014 they considered the weak separation. And okay, they proved two nice results. So first of them, if you take the random graph GNP, then such a graph you can separate by 48 times n passes. Okay. And the second special case which they proved was that if your graph has a linear minimum degree, then linearly number of paths again suffice. Okay, but there was this condition that your graph has to have a linear minimum degree. Okay. Now the other group was Balogh, Csaba, Brian Martin, and Pluhar. Okay. And again, what they proved, among other results, they consider again strong separation. They prove for GNP that linearly many edges are sufficient for strong separation. And they did some exact result for some special classes of graph.
When you say GMP, P is constant, or
P has some reasonable range, right? From constant all the way to something more than 1 over n or log n over n. All right. Okay. And well, so nice results, but both groups independently concluded that regardless whether you consider weak separation or strong separation, the correct answer should be that linearly number of edges suffice always. All right. So, okay, and nothing happened for a while. And it just happened that about a year ago, we started to work on this. And as I said, we worked on it. It was going somewhere, but truly not to the linearly number of passes. And then one day in November last year, I think, Letzter posted a paper on the strong separation, and she proved that n times log star n times some constant edges passes suffices. Okay. If you haven't seen log star, this is the number of times you have to take log in order to get numbers smaller than 1. Okay. I remember still that day. I opened archive. This appeared. I looked at it. My heart sunk. It's a beautiful paper. It's very cleverly done. So what she does, she uses machinery that Hong started about the expander, and got inspired by Matja Butchis and Richard Montgomery working on some other problems. And so what she proved is that if you have a graph on n vertices and average degree d, okay, so if you have such a graph, then you can find a subgraph G1 whose average degree is polylog of d, with the property that if you remove the edges of G1 from G, then this graph can be decomposed. Strongly separated. By linearly many edges, linearly many paths. Okay. And then of course you just iterate this until this graph will have only linearly many edges, and then you go down. Okay. So that was this result. It's 35 pages of beautiful mathematics. And absolutely not clear how you get rid of this log star from the proof. Yeah? And so what I really want to tell you today is about how you get rid of this log star. But
Can you say again what log star is?
so log star is a number of times you have to take log until you get to a number smaller than 1.
Smaller than 1? Then 1?
1. Yes. So this proof gives it, right? So you remove this you remove this graph, you separate it by the harmonic part, then you take a G1, it has now average degree polylog, right? And then you start to iterate. Apply this result on G1, this degree will be polylog of polylog, and you try to get this D to something very, very, very small. Until you can just take individual edges as a separation system. All right. So I would like to show you the following theorem. So this is due to Mark Bodami, Fabio Butler, Francois Dross, Tassio Naya, and myself. And what we prove that 19 edges suffice.
Edges or paths? Or
If I said edges, I usually mean path. Thank you. For every edge. Okay. So I would like to convince you about this.
This theorem is for strongly separated.
What's it?
This theorem
This
is
will be
strong-
for strong separation and hence for weak as well, right? All right. So proof will be by induction. So of course you can start by any, but truly for n equals 1 to work, if you take larger n and your graph is empty, or has less than 19 n edges, then of course there is nothing to prove, you just take individual edges. So you assume actually your graph has many edges, and it is, it's not empty. All right. So what do we do? So what we do here is we take the longest path P in the graph. Okay, and I will assume it starts from some vertex u and ends in vertex v. So I take the longest path that I can in the graph. Okay, and then I will take the some set S of vertices, and this will be the set of all possible endpoints of the path then you can get from P by Pluhar rotation. So let me just explain you first what we are doing, and then we can write formal definition. So this is my path. This is U, this is V. For me, I will fix this vertex V, and I will do the following. Okay, it's the longest path. So this vertex U, all its neighbors must be back on the path, right? Because it was longest one. Okay, so imagine, so this is one of the neighbors. This is vertex X, and this will be vertex immediately preceding here, this vertex. So this will be X minus. So if you have this, then of course you can find a new path that starts in X minus, go all the way to U, then to X, and then continues to V. Okay? So this set S will be the set of all possible endpoints that you get from this original path by applying Pluhar rotation as many times as you want. Okay? So surely this initial vertex U will be there because you don't have to do anything for that. Okay, so let S be the endpoints of passes obtained by Pluhar rotation. From P. Okay? But the only restriction will be V will be fixed, and I'm only rotating on these particles. So S is not empty because this initial vertex U is there, but yeah, we don't know how the graph looks like, so we don't know anything else about that, about this. All right, so why do I want this set? Well, it has some nice property. So what's the nice property? Okay, so I would like to look at the neighbors of set S, but I want the neighbors which are not in S. Okay, so this, I will abuse this notation a little bit. It will be the set of all vertices not in S with the property that there exists a vertex in S such that xy is an F. Okay? And why? Well, because there is this nice fact which says that, okay, if P is the longest path, okay, then we can estimate the number of these neighbors. It will be at most 2 times that. Okay? And essentially, what you prove when you prove this is that the neighbors of S are actually neighbors of S on this path P. Because they are on the path, you can have at most 2 neighbors, and that's what gives you this upper bound. Okay, so this is we will need this particular statement. All right. So now we have our set S. So what we're going to do? So we take H to be a subgraph of my origin graph G induced by edges with at least incident to S. Okay, so I take all edges which have at least one endpoint from S, and I take all this. Okay, I take all of them and I will put them to H. Okay, and then what we do, we will remove from this graph G S. Okay, so I will split my G into H and G prime. Okay. And about H, I will know something because of the way how I define and because of this statement. And I don't know anything about G, but on G, I will apply induction. Okay? All right? So by induction assumption, okay, if you look at G prime, this has separating system with at most 19 times number of vertices of G prime, okay, but that's M, and we remove S, so size of S. So with this many paths. Okay. Now it's important to realize what does this system separate from, right? So this system separates edges of G prime from edges in G prime, so we can separate one edge from there with another one. And it will also separate edges from G prime from edges in H, because I will not reuse these edges at all, ever. Okay? So I have a separation G prime from G prime and G prime from H. Right. So we have to do it always both ways. All right. So what we want now is we need a separation system of size at most 19 times size of S for this graph H. Okay. All right. So how am I going to construct it? Well, I have to do first some cleaning and then something very nice. All right. So first of all, I will take and look at the edges which are in P and also in H. So I want to take care of the edges such that both endpoints of these edges are on the in this hyperbola. Okay, and I take each of this edge separately as a separation system. Okay, so number of these edges is at most 2 times S, right? Because I take them from the every vertex on the path has degree 2, so I cannot add more than that. Okay, so this system will separate these edges between themselves because those are individual edges, and from everything outside. So that's good. Okay. All right. What's next? I will remove these edges from my hedge. Okay. Great. What do I know about this? Okay. So first of all, how many edges have this graph? Oh, sorry, how many vertices has this graph? Well, surely as many vertices as original graph H. And how did I get H? Well, I took S, then I took all the neighbors in G of S, but this was bounded by 2S, so this number is bounded by 3S. Okay. And so what do I do then? Well, okay. Now, this H prime can be decomposed into 2n prime over 3 passes. Okay. So I quoted earlier result of Lovar's, which implied that you can decompose into n prime passes. There is some improvement of the result, which requires only 2/3 of these passes. Okay. And this number is bounded by 2/3 times 3s. So I only need 2 times size of s passes to decompose this H prime from. Okay. But now, why do I want to do it? Well, I denote this system by D. Okay. And this system D separates H prime from PS. Okay. Okay. So PS separates PS from PS, and it separates PS from H prime. Okay. But I also needed to do it the other way around. So I decompose H prime into this many passes, and they separate H prime from PS. Okay. So how many passes did I use up? Well, I use up 2s passes over here, 2 times size of the passes over here. I still have a 15s passes left. What do I need to separate from what? I just need to separate H prime from H prime. Okay. Everything else was already separated. Okay. So how do I separate H prime from H prime? Okay, so how does this edges of H prime look like? So you have this pass P, and if you think what we did, the only edges that are left are edges of this form. Okay. Anything that just touch P on one vertex, that was taken care of. Everything on the path that was from H prime, possibly from H, was already taken care of by this PS. So the only edges that we are left are sort of with both endpoints of P, but not on the. So all the edges that we need of H prime are of this particular form. Okay. And so what do I do with these? Okay. So let me draw P one more time. H prime has n prime vertices. Okay. And I go along this path from left to right, and I will mark my vertices. Okay. I don't know how many vertices are in between, but I go from left to right, and I will mark all of them. what I will do is that I will collect these edges together to some nice matchings, and from them I will construct some paths. Okay. All right. So for every k between 1 and 2n prime, mk will be the set of all pairs vi, vj, such that it's an edge of h prime. Okay. And I plus j is equal to k. Okay. It looks odd, but so now it should be clear why am I going to do it. How does this mk look like? Well, it might be empty. You might not find any pair that I and j sum up to k. Okay. But if it does, how does it look? Well, okay, here will be the first one. So you have I, and you have a j, and I plus j is equal to k. Okay. If you take any other that sums up to k, it will be either here or here. There will be non-crossing, so it will be this range. And it's also clear that every edge is in one mk, right? Because if you take any edge in h prime, then surely this edge is in m of I plus j. And I plus j is at most 2n prime. Okay? So this is the decomposition of all the edges of the of h prime. Okay? Well, now for k, which is between 1 and 3n prime, I will construct something similar. But here I take pairs vi, vj. Again, restriction is that actually there must be an edge of h prime, such that I plus 2j is equal to k. The same idea, just different restriction. Again, every edge is in one of them, right? Because I plus 2j defines exactly k. So again, you get a decomposition of the edges. Now, what's so nice about this? I can turn every mk to a path, right? I take all these edges like I have them, and then I will use this segment to connect these two edges, and this segment to connect these two edges, and I can do this as long as I need. And this is a beautiful part. I don't care that I'm reusing edges from the path P, because I'm already separating them elsewhere. I just use them really to hook up this matching to a path. Okay? So the point is to distinguish between these rainbow edges, right, that are kind of crossing. So using this trick, I can convert this to at most 2n prime passes. Okay. Using the same trick, I can convert this matching to 3n prime passes rk. Okay. So how many passes I constructed altogether? We constructed 2n prime plus 3n prime passes at most. Some of them might be actually empty, so I don't care. So this is 5n prime, but 5n prime is at most 5 times 3 times size of s, which is 15s passes. So I constructed this many passes, and somewhere I said that we have left this many passes. Okay, so the only thing I didn't tell you is why these passes separate edges of H prime. So what would happen if you find two edges which are not separated? So every edge is in 1 pk, and every edge of H prime is in 1 r. Okay. So if I find two edges which are not separated, what does it mean? So I take Vi, Vj, and Vi prime, Vj prime in H primes, and they are not separated. So they must be in the same pk, and they must be in the same rk. Right? What does it mean? It means that I plus j is equal to k, and that's the same as I prime plus j prime, right? Because they are not separated by two different passes, and they are not separated by rk's. Well, that means that I plus 2j is equal to some k prime, and that's same as I prime plus 2j. But then if you forget about this k, we have these two linear equations, and we know how to solve linear equations. We get that I is equal to I prime, and j is equal to j. Okay. And so that means we had the same edge, so everything is nice. And this is it. This is it, because this was the last bit that was missing. So ultimately, the whole trick was that you do the induction, and you need some structure like this that sort of allows you. So this Hamiltonian path in this subgraph helps, right? It just allowed you to connect these matchings together to a path. Okay? But also, in order to be able to do it, you also need to know that the vertices on this Hamiltonian path must have a bounded degree graph. They must have a bounded degrees by some constant in order to keep the linearity altogether. Because some edges you moved away and you just used yes.
So in the definition of nk, do you mean to add some condition like I less equals to j or something? Because why is that forming a like nested edges? The nk? Because
Oh, the second one? Or?
yeah, in the definition of nk. Right?
I think I can do this.
Yeah, that would do it. That would do it.
Thank you. Yes, okay. So this works. That's beautiful, resolve the conjecture. But okay, how good is this 19n? So almost instantly I can tell you that surely it's not optimal. Okay. So at some point, somewhere we use that, for example, every graph on n vertices can be decomposed to at most 2/3 of n passes. So conjecture is that actually it should be n plus 1/2. That's a conjecture of Gauss. So already, if that conjecture is true, then surely 19 is not better. If you go through the proof, you find few other loose points. So this is surely not the optimal. So what do we know? And you will see that this is almost ridiculous how it is. Okay. So maybe we get to some questions. So this paper by Jozef Balogh and co-authors. Okay, so among other results, they prove that if you take any epsilon between 0 and 1/2, and you take n large enough, but if you take bipartite graph, complete one, where one side has size epsilon m, and the other side has 1 minus epsilon times n. So this is n vertex graph, and it requires 2 times 1 minus 2 epsilon times n path for strong separation. So we can get arbitrarily closer to 2n. I don't know a graph that requires 2n paths to separate, strongly separate the edges. So the question is, can every n-vertex graph be strongly separated by 2n edges, 2n paths? Okay. It'd be nice to know a graph for which this is not true. Now, this proof surely doesn't get you all the way to 2n. You have to do something better. Okay. Now, as for the weak separation, the question is that it's still entirely possible that 1 plus little 1 times n passes s in. Okay. It would be nice to sort of see distinction between weak and strong separation is found. Okay. So why do you assume this bound? So if you take Kn, so you can do some counting argument and show that Kn needs, for the weak separation, at least n minus 1 path. Okay. Now, if n is prime or prime plus 1, then we know that n path is enough. But in general, even for the complete graph, the best upper bound is 21 over 16 plus little over 1 times. Okay, so even for complete graph, we don't know whether n path is enough to separate them. And I would like to give you maybe.
Whose result is that? 21 over 16?
I think her name is Galinda Wykes. She is at Queen Mary in London. The paper is on archive. All right. So when we work on this problem, and at some point we had the idea that would give us this result if we knew to answer the following question. So if you, I will give you a question. If you can resolve it, you found another way, or kind of another way to prove the upper bound. Not with 19, not with 10, just linear. But the question by itself is very nice. So it's a problem. So you have an n vertex G, which is properly colored, properly edge colored. Okay. Can you decompose the edges of this graph to linearly many rainbow paths? So you have a graph which is edge colored properly. So any two edges sharing vertex cannot have the same color. You want to decompose G into passes that they are rainbow, right? No repeated color. Okay. And actually, you can even consider a weaker version of it. We couldn't even do that one, not decomposition, but just color. Right? So you can repeat edges on the passes. Okay. So we had some reduction of that previous question to this problem, but we were not able to prove anything about this. That problem got resolved. This question stayed, and it kind of feels very nice, but I have no clue how to approach it. Okay. Okay, and the final one, and I would like to stop with that one, is, so there is some, again, it's all conjecture of Gale. I mean, Gale has a number of connections of this form. So one of it is, again, every n vertex graph, which is connected, can be decomposed into, at most, n plus 1 over 2 ceiling path. Okay? And so there was this one result that I quoted by Loas from 68, okay, and which is sinusoidal related. So at most n half path plus cycles, which by division of the cycle into 2 gives you n most n path. Okay, so we use this at the beginning of the talk. Okay, and then in the main proof, we use the result of Dean and Konider, who proved that at most 2n over 3 paths suffice for the composition. But this is sort of halfway to get to the n plus 1 over 2. If you want some very nice problem, Gale had the whole range of questions that are very innocently looking and very difficult to answer. All right, so that would be it. Thank you for the question.
So any questions?
I guess there's some motivation for this problem. Maybe some algorithmic motivation or.
I don't know. I think it just gradually happened that there was this initial question by Ren, and then they started to see how to make the question more interesting after those 2 simple problems were resolved. And then first was the set theory modification that you impose some size restriction on the f, and then maybe they started to add, okay, so what if I take this A to be more interesting? You put some underlying structure, and then maybe you can get away from this law, right? I mean, you can make this constructive, this set S you can find in polynomial time, and then everything you can decompose. Yeah.
In your paper, you said if we can improve the factor 1, the label of S, yeah, if we can improve the vertex of H, the n prime, then the 19n can be improved. So I wonder, for factor 1, do you have some good idea to improve this at most 2 times S? Because in many papers, they have used the method of the Poisson rotation method to try to use it to prove some other result, like Ramsey number and something. So if we can improve the upper bound of this one, then maybe many results can be improved.
Yes, but I don't know how far you can get, even if everything works as you want. Right, so, you know, I still don't feel that you can get anywhere near 10 and right overall. So to get, I mean, okay, we still don't know any graph that requires 2 n passes,
Yeah.
and I have a feeling that whatever you choose your dream properties here, if everything works, I still don't have a feeling you get below 10n. So honest answer would be maybe the better thing would be try to come up with a new idea how to address this question altogether, because I don't think this will get, I mean, that's my opinion. I can be proven wrong, and I happily will be proven wrong, but I don't think using this you will get to 2n or whatever the real answer is. But that should not stop.
So does it make sense? I don't know if it makes sense. Can you introduce the number of edges as a parameter?
I didn't try.
You'd have to fix the number of vertices and the number of edges simultaneously, right? If you just say number of edges, it would become the original separation problem. But like you have a fixed number of vertices and a fixed number of edges, and
I've seen some lower bound at that time. That if you have a graph, then by some counting you need at least this, right? But usually it's some function of number of edges over some function of number of vertices and.
well, okay.
Yeah.
Because I was just saying in the original problem, n is number of elements.
Yes. Yes.
Here, n is not number of elements.
Yes.
So it makes sense to maybe put in the number of edges, which is the number of elements that you're trying to separate,
Yes.
right?
Yes. Yes. But I don't know how much what you get out of it, right?
No,
I mean,
I
not
don't know
obviously.
either.
Right, it's-
Okay.
yes.
So, if the graph has a Hamilton path,
Yes.
does your method give something like 6n? If you just take a decomposition of this path and then treat it as, and then just use the last step of decomposing it?
Might be. Yes.
Do you know, for that sub-problem, for that last step, do you know how optimized this, this factor of 5 is?
No.
Because it seems like a quite natural question. You're sort
Yes.
of decomposing all possible arcs
Yes.
into these nested sets,
Yes.
and such that it's separating.
I mean, but I didn't spend too much time
Sure,
thinking
sure.
about it, right? Just
Yeah.
because.
Yeah, I mean, this is, yeah,
Yes.
yeah, it's a nice argument.
If we assume that G is maybe 3 connected, then is the edge sets of the cycle, can you find a certain number of edge sets of cycles separating the edges? Is there any reason for
Not that I know of. Yeah, I did not think of that.
Right, should we conclude? Okay, let's thank this.